In this screencast, I just want to go over a couple of things having to deal with rate and specifically reaction mechanisms. Also, in your review packet, I do have one page that is turned backwards. So there were some slides that go along with Big Idea 3 that looked like they were in Big Idea 4. So I just wanted to explain that to you guys. Sorry about that. You can just flip it around in your notebook. So reaction mechanisms, so this is when a reaction occurs in multiple steps. And you would add the steps together in order to get your overall reaction. But for writing the rate law, the rate only depends on the slow step. It does not depend at all on the fast step. So in this particular problem, we have that rate is equal to K times the concentration of A squared times the concentration of B. And they want to know what the intermediate is. And it would not appear in that rate law expression at all. And which of the following mechanisms gives this rate law? So if we look at mechanism number 1, we again, of course, would go to the slow step. The slow step would be R equals, or the rate law for the slow step, R equals K, concentration of E times the concentration of B. Well, E is an intermediate because it happens in the middle. It is formed in step 1 and used up in step 2. So it happens in the middle. And we can't have intermediates in our rate law expression. So we have to substitute it out. So we go from where the intermediate was formed, so that is step 1. It is fast and it's at equilibrium. So that means the two processes, the forward reaction, the rate of the forward reaction is equal to the rate of the reverse reaction. Rate is, for the forward reaction, would be the constant K times the concentration of A times the concentration of B. And the reverse reaction would be K times the concentration of E. So the concentration of E is equal to the concentration of A times B. So we can substitute that in right here for E, and our rate law becomes K, again, that's where we had the K1, K2, K3, K4, K5, but that doesn't really matter. A times the concentration of B, because that's what E's rate is equal to, times the concentration of B, which came from the original slow reaction. That does not match the rate law expression above, so it cannot be reaction 1. So, or mechanism 1. So let's look at mechanism 2. Again, we're going to go to the slow step. It's going to be R equals K, concentration of E times the concentration of A. In this case, again, E is an intermediate. It's formed in step 1 and used up in step 2, so we need to go to the step that formed the intermediate. This is fast and at equilibrium, so that means the two processes are happening at equal rates. This happens to be the same as in the fast equilibrium step of mechanism 1, which I wrote the rate law expression right here. If it was different, I would just write it again. So now I know that the concentration of E is equal to the concentration of A and B. I'm going to plug that in right here. So that's going to be K, concentration of A times the concentration of B times, because that's what E is, times the concentration of A, which came from the original rate law. That does match the rate law expression that was given. So 2 does qualify. So let's check. Mechanism 2 does work. Mechanism 3, we go to the slow step, and it's going to be R equals K, concentration of A times the concentration of A. There is no B in that one. There is no intermediate in that one, so it cannot be reaction 3. It has to be reaction 2. All right. The next thing I'd like to go about or talk about are what reaction mechanisms look like in energy diagrams. All right, let's get rid of some of this stuff here. All right. right, so we have these energy diagrams. What I want you to understand with each of these energy diagrams, the number of hills that you have correspond to the number of steps in the reaction mechanism. The height of the hill corresponds to the slow, whether it being slow or fast. Slow reactions have a really high activation energy. It takes a lot of energy to break those bonds. And in every reaction mechanism, I said it is a hill because in every reaction, you've got bonds breaking and bonds forming, even if it is just an elementary step of the reaction. So you can count the number of hills to see if we have to see how many are in the reaction mechanism. So if we look at A, it says that it is exothermic. So an exothermic reaction, that means that it releases more energy than it takes in. So it's going to look something like this, where the reactants are at a much higher potential energy than the products. So that eliminates, means it's not going to be this one. It could be this one because we've got two steps. It could not be this one because this one's going to be exothermic. This one only has one step because there's only one hill. This next one has two steps, but it is endothermic. Or it could be this one. So then we need to look at the first step is slow. So that means the highest hill has to be on that first, or the tallest hill is that first one. All right, so we've got it down between these two. In this reaction, the first one is pretty short, and then the second hill is way longer. So our slow step would be the second one. So it can't be this one. It has to be this one right here because our first reaction is much slower than our second step of the reaction mechanism. All right, so then if we look at B, we have an endothermic reaction. Endothermic reaction should look something like this, where our reactants, it took way more energy to break all those old bonds than what was released when we formed those products. So the products will be higher than the reactants. It is again going to be a two-step mechanism. So I can get rid of this one and this one. And then we also needed endothermic, so that means it can't be this one. All right, and the second step is slow. So we need that second hill to be the highest. So quite obviously it is going to be this one right here. The first reaction's much faster than that second one because it takes time to collect that much energy. All right, then we look at C. It's going to be exothermic, so that means it is going to release more energy than it took in. And it is a two-step mechanism where the second step is slow. So we need, it can't be this one, it can't be this one because it's got two steps, it can't be that one. So it has to be this one. Let's make sure it has two steps, so two hills, and the second step is slow. That does qualify this one. The second step did take quite a bit longer because it has a higher hill for that one. All right, then we look at D. This one is endothermic. So again, what's going to happen here is it took in way more energy than it released for my reactants, from my products. And so it can't be this one. It's got two steps. And the first step is going to be slow, so the first hill has to be higher, and I think the correct answer is this one. That first step is going to be the slower because it is the taller hill. All right, then we get to E and F. These both have one step in them. The first one's exothermic and the second one is endothermic. So exothermic is where the reactants, it's pretty easy to break those products, so it took in way less energy than it released. So this is going to be exo, and that means that this one has to be E, and this one is endothermic for F, so this one has to be F. And I think if we scroll through these, that's what we get.